In this video we are going to learn the basic structure of the vhdl code and the difference between signals and variables, and a brief introduction on process and types of port available in the vhdl code and their uses, and a basic adder program. Before starting going with the structure of the vhdl, I would like to introduce you to a new site called the EDA Playground. This is a place where you can play with your codes, and there are like many languages available, system Verilog, vhdl and stuff, and then you can simulate your code with one of the best simulators available in the market. Let's go to the point now. So a basic structure of a vhdl code contains the entity declaration, which define the input and output model, and then the architectural body, which describes the operation of the model. So this is how a basic skeleton of a vhdl code looks like: entity name, and then port, and then for this thing I'll write the port, entity name is, and then in the next line you get port, and this is the place where you define all the input and output ports. So this is a basic uh, program of an adder. So a basic program of an adder contains, this is a black box of an adder, which has an A. A is an input port, B is an input port, and C in is an input port, and then C out is an output port, and C is the sum. Now let's see how do we write a program for an adder. So, and this is the basic block diagram of what we are going to design inside a vhdl. So before going here, let's have a look at the different types of data types available in the vhdl. This is the mostly used data type, standard underscore logic. By default I always use this, and then you have other data types such as bit, boolean, bit vector, and integer, that you can google it out any which ways. And now architecture behavior, this is where you write how your logic is going to work, that is what is going to happen inside this black box. And now let's see how a simple adder is going to work. A very simple logic, which is nothing but process of A, B, and C in. This is the sensitivity list, we will discuss about it shortly. Begin, and then see, whenever you write a process, never forget to write begin, because when you don't write begin, you're definitely going to get an error. And C is nothing but AX or BX or CN, which is a basic equation of the sum in an adder, and then C out is AB plus BC plus CA. That's what I wrote here, and end process. And now let's see what a process is. So a process is the only means by which an executive functionality of a component is defined. For example, I have used A, B, C ports here, and if I want to write a logic for it, then I have to use a process with a sensitivity list, which is nothing but I am using A, B, and C in here, and so that I can use all of the input and output ports to write the logic in a black box. And for a model to be capable of being simulated, all the components in the model must be defined using one or more processors. Let's keep this aside, and I'll tell you this one when we are going to advanced programming. So one of the most important things, what we forget to do in process, what should we not do in process? A process cannot have sensitivity list and wait statements. We have not gone to the wait statements yet. Wait statement allows compiler to wait for a signal. For example, wait for rising underscore edge of clock. If I declare like this in a process statement, and vhdl is going to show me an error stating that this is not allowed. So please don't do that. Not allowed. Not allowed. If parameters are, if sensitivity parameters are declared. Allowed. Allowed if process has no sensitivity parameters. So this is not allowed in this case because I have parameters a, b and c in over here. And then please don't port map inside a process. When you do that, vhdl is definitely going to pop up an error. Please keep this in mind because sometimes we just keep forgetting and then just port map a component inside a process, and then vhdl pops you an error stating that no port mapping, you have to change the logic. So these are the two golden rules which you have to remember when you're writing a structural or a behavioral vhdl code. And coming on to signal and variables. So what is a variable? A variable is available only within a process. It's just like a variable in C where I have let's say for I is equal to 1 to n, where's the text box, like the variable in C for I in 1 to 10, I is equal to I plus plus. This is not vhdl again, this is just a basic example. So the value of I is updated after every iteration. So that's what happens in vhdl too. Variable is only visible inside a process, and it's only available it's only visible inside a process, and then its values are updated regularly, whereas a signal is not like that. A variable is useful if you have a rather complex, let's leave it for now. And then coming on to signal, a signal can be used to connect two different components in vhdl, whereas a variable cannot be used to connect two different components in vhdl. This is a golden rule which you have to remember. If you try to connect two components using a variable, vhdl is going to pop you an error, and it's not a very good habit to use variables in vhdl. And coming on to signal, so I have declared a dummy signal here, signal p1, standard underscore logic underscore vector 2 down to 0, which means that p1 value can lie anywhere between 000 to 111. And if you don't define it properly, it can show you xxx, UUU, or zzz, I impedance state, or whatever. And then a signal, once declared inside the architectural behavior of SAM, which means the architectural component, it can be used anywhere below the process. You can use P1 anywhere. And again, if you try to, you can use, for now, that's good. For now, that's good. And that's all for today, guys. If you have any questions or any updates about the video, you can just post it in the comment section given below, and I will try to answer them as soon as possible. That's all for today. Have a nice day. And in the next class, we're going to discuss about a basic adder program. I'm going to simulate in the Xilinx ISC. And then comes the most important part about the reuse of elements, that is use of port maps. And we will try to involve some errors in my program and try to solve it. And that's all for today. Have a nice day.